Yeah, stop. Yes.
Welcome back. Welcome back to the afternoon session. And we're starting with two contributed students. The first one is Roopayan Ghosh from UCL, and he'll speak about Entanglement.
Right. Good afternoon, everyone. I hope you had a good lunch. During this time, yeah. It didn't work. Yeah. Okay. So I'll be talking about the separability criterion using one observable, some special states. Obviously, it is usually not done by one observable, so I'm saying when it can be done by one observable, and that will lead us automatically to entanglement detection by quench. I'm working as a postdoctoral fellow with Professor Roopayan Ghosh in University College London, and the talk, the talk would be organized in something like, I'll go directly on the very basics, preliminaries, just to be complete. And then I will talk about why measuring entanglement is hard for an arbitrary state. And then I will talk about what we did, where we are saying that in certain cases it's possible to detect entanglement using one observable. And then I will conclude and give the outlook. Okay, let's begin from the very basics. What is entanglement? So when I think Einstein was the first person in the CPR paper who talked about entanglement per se, and he said that it was spooky action at a distance. So the basic idea is if you have to entangle particles, and if you, no matter how far apart you take them, if you do something to one, the other knows about it. And then there was many popular science questions about whether this is like faster than light communication and so on and so forth. But it was later realized that this doesn't make any sense because you cannot create entanglement by classical communication. So it's all quantum, but I don't like to go into all these things. So I like to understand entanglement in a slightly different manner from the formal definition, which changes your idea of defining what is entanglement to rather defining what is a separable state. So what you want to do is you want to say the states which are not separable are entangled. So now we have to define what are separable states, and that has a very good mathematical definition. Let us take, for example, a bipartite system. It means you have a system and divide into parts A and B. So a quantum system. So let's say the Hilbert space of the part A is denoted by HA and the Hilbert space of part B is denoted by HB. Then from basic quantum mechanics, you know that a composite Hilbert space will be just the tensor product of two states, which is H. Now for a pure state, which can be written as a Ket vector, which is an element of the full composite Hilbert space, it is said to be separable if you can write it as a tensor product of two states, psi A and psi B, where psi A only belongs to the Hilbert space of A, and psi B belongs to the Hilbert space of B. So it's like a separable state is a state which you can write separately in the two individual Hilbert spaces of the two partitions. And then this definition carries over to a mixed state, which a bit more complication, where instead of just one such thing, you have a linear superposition of many such density matrices. Rho I belongs to the subsystem A and Rho I belongs to subsystem B. And it's because of this superposition is what it creates problems for detecting entanglement in mixed states, which we'll come to later. Because there's a probability is obviously summation of Pi equal to 1. Okay, so that's all about the preliminaries. Now let's go to measuring and detecting entanglement. So as I told you before, it's actually very hard to detect or measure entanglement. And as far as I'm aware of, among many body experiments, very few many body experiments have actually done so. And I know of two of them, and I'm going to speak of those two only. One of them is done in 2015 by the group of Rajibul Islam and others, where they measured the purity of a system by creating a replica of the original system. They used a stream of photons and managed to split them and interfere them together and connect the number parity of the final state to the purity of the system. The purity is basically trace of rho square. So you needed like 2 copies of the system, and then you could interfere them to measure purity. But yeah, the problem with this was you needed a replica of the system because you have trace of rho squared there. So you needed a replica. Then later, in 2019, Bridges performed a set of randomized measurements in an iron trap experiment where he didn't need a replica. He had only one state, and he somehow computed a peculiar correlation function and connected it to the second Renyi entropy of the system. And I personally believe this technique is pretty similar, probably it is similar to the classical shadows technique, which people nowadays use to approximate observables by a set of randomized measurements. This is one of the ways probably they did it. And I don't know much more about other experiments which have actually measured entanglement in many body systems, but oh, thank you. Yeah, sure. So, but the important thing to note here is in both these cases, what they could measure was for pure states, entanglement for pure states. This is an important point to remember here. Now, why is it so hard to measure entanglement? It's because entanglement actually implies quantum correlations. But when you do an experiment and when you measure an observable and then compute expectation values and so on, what you're actually measuring is classical correlations, not quantum correlations. Unless you design an observable to measure quantum correlations, that's a different thing altogether. I don't know about it, but typically you measure classical correlations. So, since this is quantum, this is classical, one correlation measurement is not enough to detect entanglement. It's quite possible that you have classical correlations in a system, but then it's not entangled. What you need is for bipartite systems, you have classical correlation necessary for all measurements. For multipartite, this is a kind of a gray area, but I'm not going to go into that. For bipartite, this is the statement. You need to have classical correlation in all your measurements to say it's entangled. Now, this is actually a bit easier for pure states, as you will see again later, and hence measurement has been possible there. Because you have this entanglement entropy, which is actually a good measure of entanglement for pure states. And that is related to the purity. Because, for example, you have a pure state, you trace out a part of the system, it becomes mixed, which is what purity actually measures. Then obviously the system was entangled before. But if you have a mixed state and then you trace out, it still remains mixed. You can't really say anything about it. So these kind of measures don't work for mixed states, and that's why there is no easy way for them. And that's where the problem lies. So here's an idea. So I just said that classical and bipartite entanglement means classical correlation in all measurements. So why don't we just find the observable which detects no correlation in separable states? If you could find one observable for all separable states which detects no correlation, we're done. We'll just measure that and we can detect entanglement. But the reality is there is no such common observable for all separable states. And what that does is you have a zoo of something called entanglement witnesses, which detects entanglement, does not measure it. And it detects for specific classes of state or for specific states. So, and the point is it does not cover the set of all states. And so we do not have a foolproof detection method yet. And it's now described as a non-polynomial hard problem. So let's see what this means pictorially. So as I was telling you, witnesses detect entanglement and its witnesses are good because they are kind of trying to relate to what you actually measure in experiments, like correlation or something. And they detect entanglement by, they have some lower bounds and upper bounds, so they have some predefined cutoffs. And beyond, if you have this value beyond that cutoff, it says that your system is entangled. So pictorially, let's say I am, can I see the colors here? No, very bad. Anyway, so the point is that if you assume this full circle is the set of all states, I'm trying to represent it here with a schematic diagram, and your entangled states lies here, and separable states is here because it's a convex set. And these are some peculiar states which are bound entangled, which I have put for completeness, but I'm not going to talk about it. You can ask me later what these are. So these are kind of schematic representation of the entanglement witnesses. So what they do is, for example, witness 1 can detect all states entanglement in this region, shaded region, but it cannot say anything about the rest. And similarly, think for, let's say, witness 2 and so on and so forth. And we don't have, let's say, all the witnesses that cover the full space. So there are like some parts which is not completely not covered. And so we don't really know how to detect entanglement for arbitrary mixed state till now. Okay. Now I'm going to go to a particular kind of correlation witness. I'm not sure how to get this to mount, maybe. But anyway, it doesn't matter.
You click on the 3 dots and hide floating meeting.
Okay. Yeah, thank you. Okay. So there is this correlation witness which is popularly known as MOB. This MOB is actually an acronym for mutually unbiased basis. But yeah, so what do you mean by mutually unbiased basis? So let us assume you have two sets of bases, alpha and alpha prime, and alpha I is one element of that basis, and alpha j prime is an element of the other. So for any element of first and any element of second, if the overlap square is equal to 1 by the Hilbert space dimension, this V is the Hilbert space dimension, Then you say these two bases are mutually unbiased. And people have shown before, many people, that if you can measure the correlation of some observables in at least two such bases, then it is possible to detect entanglement for some states. It's not very good, but it's possible. There are different correlation measures, like for example, mutual information is a correlation measure, and then there's Pearson correlation, which is a good correlation measure. And apparently, Pearson correlation is one of the best for these cases, so I'm going to talk about that only here. Which is basically, let's say you have a system S bipartitioned into O and B, you have an observable OA measuring something in bipartition A, and OB measuring something in bipartition B. Then Pearson correlation is simply the connected correlation divided by the variances of the measurements. That's your Pearson correlation. So you do this, and then you find another observable for two subsystems, OA prime, whose eigenbasis is mutually unbiased to OA. So this is something called like a mutually unbiased observable to OA. Similarly for B, you have another OB, which is mutually unbiased to the first one. Then they have shown that if you fulfill this condition, where this PO plus PO prime greater than 1, then this is a sufficient condition for entanglement. But unfortunately, this is not necessary. So this doesn't work for most of the entangled states, and it works for only states which is like close to the maximally entangled states, and that's why it's not very good. People have then tried to add more and more such measurements to try to improve it, but even then it doesn't work for all states. So this is a problem. So you can measure, one thing is you have these correlations, which is easy to measure in experiments, but then you cannot really measure entanglement very well. So, yeah.
So when you say entanglement detection, do you mean like can you quantify the entanglement of the state, or can you just say that this state is entangled?
Just the state of entanglement.
So you can't really check two states and then measure
No.
quantify it.
Because I'm with mixed states, and for mixed states, there is no real good quantifier for entanglement. That's why you're just trying to say whether a mixed state is entangled. Now starts what we did. So, okay, if you cannot really say anything much about the state already, so why don't we try to reduce the number of measurements we're trying to do and see how much we can say with just one measure. And so what we're trying to see is whether there is what is the possible one observable entanglement detection? How much, for what states is this possible? So this is the question, how much can we tell from just one measure? So in certain scenarios, it's not rare. If you measure the correct correlation function, it can tell for the entanglement system for both pure and mixed states. But the point is, the pure state case is not really relevant for entanglement detection. You want to measure there because it's quite trivial to detect entanglement for pure states. Because you have this particular correlation function, and if this is 0 somehow for your measurements, unless you're measuring some pathological stuff and all the expectation values are already 0, don't do that. Some non-zero expectation values of these states, then this is a necessary and sufficient condition for zero entanglement functions. Any correlation function giving 0 means it's separable. And this comes directly from a definition of pure states, pure separable states. But for mixed states, it's trivial in few, but it's generally difficult. Let me tell you why. Because you can get correlation for separable states as well. And the best example to show this is this classically correlated row Cs. So how is the state formed? So clearly, this is a tensor product of two kind of density matrices. So this is the separable state. So alpha is our eigenstates of the observable OA, which acts only on subsystem A. And beta is the eigenstate of observable B, which acts on subsystem B. And this is a classical correlation. Now, if you measure C1, which is this particular quantity, you will find that it gives you a large non-zero value. But then, clearly, this is not entangled. So this is telling you nothing. But then if you measure C2, which is like we're measuring the correlation functions for the observables, which is mutually unbiased to C1, then it will give you 0. But then how to decide if you don't know anything what to measure? That's the question. Yeah, I know it's live stream, not a problem. So how do we decide? So let's be a bit more general. So remember, I told for the entanglement for a generic separable state, you have pi rho I A cross rho I B kind of state, a summation of many such states. And if you compute for a general observable, if it's separable, then it comes out to be something like this, which is just trace of this into this because it's separable. It just works on two different little spaces. And these two come out units. But if pi equal to 1, so let's say you have only one, I can only take the value 1 value, then this is fine because this will give you just these two multiplication and this is also this multiplication and thus gives you 0. Fine, you're good. Separable states are giving you 0. But if that's not the case, if you even have two such states, then it's not good because here you have, let's say, two terms Well, here you have 4 terms. The cross terms will not cancel. So you're going to get a non-zero value of correlation. And that is the problem for mixed states. That is why you cannot detect entanglement easily with correlations for mixed states. Okay. Is there a loophole now? So imagine if you could find some observable which did not depend, which gave you a value which does not depend on I. Like some observable which always gives the same value no matter which such state it operates on. Then, in principle, you could just take this out. It will just some constant times summation pi, which is 1. Here also it's the same thing, and it will give you 0 if it's for separable states. That is a loophole which we're trying to exploit. But be careful, one observable which does it is basically the identity matrix, but you don't want that because identity will give you 0 even for mixed states. That's totally wrong. And as far as I'm aware of, generic observables does not exist, which gives you, if it did, then it's not an NP-hard problem anymore. So it does not exist. So can we find some classes of states where we can do this? And that's what we did. We found it possible for 2 classes of states. I'm sure there are more. I'm going to find it later, but there are 2 classes of states where this works. Let me take a sip of water. Okay. This first class is actually, if you think deeply about it, you will understand that this is actually quite expected. So this class is a state which has a locally conserved charge. Let's say magnetization. And we measure the conserved charge after a specific quantum quench. So you have this magnetization conserved in the system and measure this magnetization of the 2 halves, measure the correlation between them after a particular quantum quench, which I will tell what it is. So quantum quench is just like you have a state, but you're evolving it with not, let's say, a Hamiltonian with general whose eigenstate is that state. That's basically a quantum quench. And this is interesting, but interesting for experimentalists, but this is more interesting to me from a theoretical perspective. Because if your system was separable to purely real or purely imaginary state, it was never the case anyway, but still it was. And if you have an observable, which is diagonal in your computational basis with this kind of property, it looks very weird, but let me tell you, it just means that the first and last elements are like negatives of each other and so on. This positive is for imaginary and negative is for real. For example, let's say you take the SZ expectation value, that's like +3 -3 and +2 -2, this kind of observable. If you measure this correlation of this observable between the 2 systems after the specific quantum points, which I will come, then you can actually say whether your system is entangled or not. How does it work out? And what is the quench? What is the quench? For a string of qubits, the quench is actually quite simple. It's a completely local quench where you use a sigma x operation on each side, and you act on it for a pi by 4 time. So, and for qubits, which is more general. It's a more non-local transformation, which is related to the many-body Fourier transformation, but with an extra phase, which is actually important. And this also works for qubits. So that means this is not unique. But the common feature of both is this both generate MUBs to your original computational basis. So you have a specific MUB where this is working. So not all MUBs this work. These are from specific MUBs where this works. And the proof which I did was actually completely algebraic. I don't really understand it from the deeper maths behind it yet, but algebraically I can show that for, let's say, for the qubit case, there are certain properties of U for this first, let's say, this first one, which is this simple one. For this case, the certain properties which helps us to show that for any arbitrary completely real or completely imaginary rho A, this will give you a constant value. It doesn't matter what rho A you choose. And the properties are like, so first one is very simple because sigma x transpose equal to sigma x, so this UT transpose is equal to UT. This is a bit trickier to see, but you can just do some sizes and then you will see it immediately that if you take a particular column index, then the first and the complementary row, the first and last, second and last, to multiply those elements, then what you will get is just a phase which is independent of the row index. And third one is each element is just some integer power of e to the power I pi by t. So I'm not going to go into how this works, but if you do the maths using these 3 properties, you will get that this particular operation, this rho prime A is just u rho A u dagger, because that's what you're involving, the quench, basically. into this OA, which I defined before, a specific OA, it will just give you a constant factor, which is just dependent on the factor of OA. And when you get this, that means that this particular quantity will give you 0. And you can again show that for mixed states, because this is not equal to this, it will give you a non-zero value. And this condition is important because when you prove it, you will actually see that you need to use either symmetry or antisymmetry of the density matrix, which for a generic Hermitian case, it doesn't work. So that's why, because you're choosing symmetry or antisymmetry, that means that's either real or imaginary. Okay. So now what we have shown here is that there is, for these particular conditions, I have this to be 0 for all separable states, and we can again show that it's non-zero for mixed states. The other case for the conserved charge is more intuitive, because, for example, you have this locally conserved charge, that's a magnetization, you measure it into half of the system. You know that the magnetization of one half will be the total magnetization minus magnetization of the other half. So obviously, if you measure the Pearson correlation between these two values, it will invariably give you 1 because it's linearly related. And then if you recall the first formula where I showed PO plus PO prime greater than 1, if PO is equal to 1, then obviously PO prime has to be greater than 0 for it to be entangled. And that means that if you just measure any mutually unbiased observable there, then that is enough to detect entanglement if it shows some correlation. You can prove it using the quench itself as well, but that's more involved and it's not necessary either to understand what's going on. Yeah, okay, I'm almost done. This is the just example. So for example, I choose a very complicated looking Hamiltonian because I'm giving you one example where I've done the particle conservation, because in examples where I don't have particle conservation, it's a bit more tricky. It's there in the paper here. So you can read it if you want. So here I chose the example of a Heisenberg model with an on-site field just to make it more general, but I didn't want to do random averaging, so I chose a quasi-periodic potential here. And I chose density matrix, this give state, because I don't want to do trivial pure states. And then what I find is that my measure C2 and this negativity, which is what people usually use for mixed states, this partial transpose positive partial transpose criterion and so on. It kind of agrees. I mean, of course, I'm not saying it's a measure, so it's not going to be same, but at least where it's non-zero, this particular point where it's 0, which is another physical thing which we need to understand, which we have, is probably there somewhere in it, why it's 0 here. But anyway, the point is it kind of agrees, and as you can see, as we increase beta, it's kind of actually qualitatively agreed as well. This blue and red lines are also like moving in a similar manner and so on. And this one is when we use some Lagrangian evolution again to try to keep it all mixed and so on and so forth. And you can see that it again qualitatively agrees. This P2 is the blue line, and which is this line. There's this entanglement barrier feature, which again happens and that requires more explanation and so on and so forth. And this is the disorder strength. And the main takeaway message is our thing is, and negativity agrees in these cases.
Sorry, what
Yeah.
W in these points?
Oh, so W is, thank you for that. W is the strength of the disorder which I'm choosing, which I chose a quasi-periodic disorder just to prevent averaging.
Okay.
Yes. So I'm just saying that, okay, even if I add this, nothing changes. That's just some sanity checks. Yeah. So what did we achieve really? So in vacuum, okay, all these things. So we have all this vacuum meaning. I'm just saying that when we don't know anything about the state, what we do is, for example, we knew this part is entangled, but we didn't know anything about this part. But now we have said that we have devised a method to kind of understand a part of the state which is separable. So that's how, like, if you don't know anything about this, at least know something about these states. So this is what we additionally did with baby steps, but it's still an improvement of what we know now. And yeah, that's it. And I'm done. So conclusion is these things. So what I'm just going to say here is for charge conserved systems, it's very easy. For not charge conserved systems, it's possible, but we have to do some more juggling of like lower cutoffs and stuff. And so everything which I've told you here, I've just done an algebraic proof. I'm sure there's a deeper understanding. There is some hidden conservation law or anything which I'm missing because it's reality and imaginary condition signify something which I don't know yet. And you want to ask me what happens to multipartite entanglement? I'll tell you to be careful there, because I've seen papers which has chosen some correlation, classical correlation measures, and stated that quantum correlation exists without classical correlation for multipartite systems, which I'm not so sure of. So I'll just say that we have to choose the correct correlation measure and then repeat this process to really understand about multipartite. And it's just up on archive today, and thank you for your attention, and I'll be happy to take questions.
Thank you very much. Mentioned that so you can detect this bound entanglement.
That I don't really know it yet. Actually, I can detect this is actually a separability criterion more than entanglement detection. So usually entangled witnesses detect entanglement. What we're doing is the reverse. We're trying to detect separability. It won't detect the bound entangled states of separability. That's I can tell you that. But it cannot really say unless without the aid of other entangled witnesses whether a state is bound entangled or not. But yeah. Yeah, I know. Bound entanglement is very tricky, and yeah. This is all I can say.
The fact it follows this negativity so closely seems to suggest
It cannot do it. Yes, but the thing is, I'll tell you what happens. So if I take a bound entangled state, it will detect it as entangled. Okay, but the problem is my criteria is about whether it's zero or not. If it's non-zero, I cannot really say anything because it's a separability criteria. That's why. So I've been trying to. So when I first did it, I tried to make it more general, like find an observable which can do everything, but then I could not, so it ended up being like.
Let me ask a stupid question. Your body is at a finite temperature, and by the eigenstate thermalization hypothesis, it's entangled with the rest of the universe.
Yes.
So why do I know whether it's entangled? It's obvious.
No, I mean, so for example, these gravity experiments, which people try to say whether it's quantum or not, they try to entangle two bodies and decide whether they actually get entangled by gravity.
Seamus is doing. Yes, yeah, and what?
Then if it's entangled, then gravity is quantum. So you have to find an easy measure of entanglement, because if it's a mixed state, you don't really have a good measure. That's why.
But what's the counter argument to me saying that you must be entangled with the rest of the world? You could probably say, how do I know that? I could just be in a mixed state. Would that be your answer, counter?
Yeah, maybe.
Answer.
Yeah, because for pure states, like I told you, yes, you know immediately if it's correlation, there's entanglement. For mixed states,
Got
you don't. Yeah.
So we said the probable states, you meant that there's some unitary that connects the states with the particle.
Sorry.
When you define separable states, you
Yeah.
meant how states that are connected to the product state by some unitary, right?
Kind of, yes, locally.
Okay, so I didn't know this, that there's some like the witnesses would be able to tell if a state is long range entangled or not. So there is some experiments you can do to say this is long range entangled.
Long range entanglement in pure states probably yes, in mixed states probably no. That's the entire point I'm trying to make. That for mixed states.
Okay,
we
because you
don't
said
know
that I also for pure states it's easy, but from what I know so far, like there's no easy.
No, you can say it's entangled or not. You cannot say how far it is entangled or how much it is entangled.
You can tell whether it's separable or not separable. That means like yes,
Yeah, that you can obviously say.
That is the same thing. Like long range entanglement means we kind of connected to separable state by.
Yeah, I mean, if you let's say you say a state is entangled, but you don't know whether it's long range or short range. I mean, this is all bipartite, right? So in principle, if you find correlation between this and this, then you can say it's entangled. That's the entire idea. I mean, connected correlation. You always can say it. That's the entire idea. But you can't say how much entangled it is. That's the point. That it's weak or strong or whatever. I'm not sure what's exactly this, because this is what I mean, I'm new to this field, but this is what I learned from the few papers I've read.
Yeah, I think that the mixed thing makes it different from short range. So yes.
Yeah. But we can talk about this later. I will probably understand your question a bit more. Yeah.
Okay, yeah, maybe we actually move on, given that we started 44. Thanks so much, Roopayan. The next talk is Alex Nico Katz from the other ball. The topic, I don't remember.
This one, right? That's the one. Okay, what's going on?
It's
Oh, it's not, sorry, one moment.
no, no worries. It's not mine.
Yeah, it's with me.
Yeah.
It's